This is a short video just trying to summarize in just a few minutes the work done in a paper published in 2019 by myself, one of my postgraduate students, Mark Hanna, and some colleagues in Swansea University's College of Science, Mark Dawson and Michele Massiti. What we were trying to do really was improve the parallelization scalability of a discontinuous Galerkin based finite element solver for the Boltzmann-BGK equation, which had been developed in previous work. This was published in a special issue of the International Journal of Computational Fluid Dynamics, and that issue was all about discontinuous Galerkin methods. So the starting point for this work mathematically is the Boltzmann equation. In some ways this is a simpler definition or description of a fluid flow than your conventional Euler or Navier-Stokes equation set, because it's a single equation. It's got a single scalar unknown f, which is a probability distribution function that describes effectively the probability of finding a molecule or particle in the fluid flow at a particular position in physical space, travelling with a given velocity, so i.e. at a particular position in what's called velocity space at a particular time t. Of course, the fact that the unknown is described across physical and velocity space is what gives solving this equation its complexity. Also, the source term, the q term you see in this equation that sits on the right hand side of the equation, is mathematically complicated. That's quite a complex integral actually hidden away in that q term on the right hand side, making this an integral differential equation, which has been another one of the sources of the challenge of solving this equation over the years. So what a lot of people do in this field, and it's what was done in this work, is to simplify the right hand side to what's called the BGK collision term. And effectively this simplification makes the assumption that as molecules in a typical fluid flow collide with each other, the effect of those intermolecule collisions is to change the distribution function of the molecules, i.e. the distribution of velocities of those molecules, from a non-Maxwellian state to a Maxwellian state. And effectively a Maxwellian distribution is a Gaussian distribution of molecular velocities. Again, if you want more details on the kind of baseline mathematical or numerical model for solving this equation, I'd recommend you go and read this paper that was published in 2011 in the Journal of Applied Mathematical Modelling, which outlines the kind of the starting point for the work done on this project. So as I mentioned, the complexity in solving this is linked to the fact that you have to discretize not just the physical space of your problem, but also velocity space across which the unknown, the distribution function, is solved. In this work, the physical space is discretized using a discontinuous Galerkin approach, where we have an assembly of discontinuous triangular cells or elements with three independent nodes associated with each of those cells, and where the cells meet at a point, rather than having a single linked unknown, you have multiple unknowns, allowing the solution to be discontinuous at the edges of these triangles. The velocity space, in principle, extends from the origin out to infinity, but of course you have to practically place a limit on the size of the velocity space, which essentially involves placing a limit on the maximum speed a molecule can travel at in the model. And this is effectively discretized using a single cell, using a high order quadrature method, in this case Lobato quadrature. Again, the reasoning for choosing that quadrature scheme is outlined in the paper that kind of this work builds upon. So you can think of the discretization of the space across which this equation is solved as being the superposition of lots of these velocity space cells sitting on top of every one of your discontinuous nodes in the physical space grid. And when you think about the implication of that in terms of the number of degrees of freedom of the problem, you realize that quickly, as we will see later on, a relatively simple looking problem ends up having an extremely high number of degrees of freedom in these schemes. Now, up until the work done on this project, the parallelization of the code had been done using just partitioning of the physical space using a classic Metis approach. And what we did in this project was to add in partitioning of the velocity space. So rather than the entirety of the velocity space being given to a single core that is responsible for a particular node in the physical space grid, the velocity space as well as the physical space is distributed across the available processes that you're running across. The paper, of course, goes into all the details algorithmically of how this is implemented in the code, which in the context of this short video I don't have time to go into, but that is all detailed in the paper. And finally, a test case across which the effectiveness of this parallelization works is explored in the final section of the paper. The case study is one of the classic cases that was used in the 2011 paper that this work builds upon, and it's hypersonic flow in a rarefied, sort of very low density atmosphere across a standard hypersonic reentry type geometry, in this case a double ellipse. So that image gives you an idea of the size of the physical space grid that we were running on in this problem. It consisted of 28,000 elements or cells in the physical space. Of course, each of those cells has 3 independent nodes, so 3 times that number of physical space nodes. A Lobato quadrature of order 80 was used for the velocity space, which in 2 dimensions gives you 6,400 nodes in the velocity space. So when you multiply that 84 or 85,000 physical space nodes with 6,500 velocity space nodes, you end up with 500 million or so degrees of freedom, even in a relatively simple problem. So the physical conditions this was run at was Mach number 25, range of angles of attack from 0 to high 40 degrees angle of attack, and a Knudsen number which defines the degree of rarefaction of the problem of 10. And this baseline case that was run across 640 cores or 640 processes took an hour and a half to converge to a steady state solution. But what is really interesting is the final part of the paper, where we explored how you optimize the partitioning in the physical space and the velocity space for a given number of cores. So if you've got a fixed number of processes available to run on for a given application, how do you decide what the optimum number of physical space partitions and velocity space partitions is? And it turns out that it's not trivial. It is inevitably linked to the architecture of the machine that you're running on, so the number of processes per node in your PC cluster, for example. So in that baseline case, you can see on the left-hand graph here, we're looking at, for each of those coloured lines, we're fixing the number of physical space partitions and then varying the number of velocity space partitions to give you the total number of cores. The dotted black line is linear speed up, and you can see in this particular application, if we ran with 16 physical space partitions, we were able to actually achieve superlinear speed up. The same data plotted in slightly different ways on the right hand side, where we're fixing the total number of cores, the number of processes we're running, and the x-axis represents the number of physical space partitions. But what's interesting then is if you change the discretization of the problem, so increase the fidelity of the problem by a couple of orders of magnitude. So I think in this case we went from 500 million to multiple billions of degrees of freedom. The behavior changes. In fact, we weren't able, because we didn't have sufficient cores available to us on the machine we were running at for this project, to push all the way to find where the optimum sits. And in this case particularly, we see that the architecture of the machine has a big influence. So the number of cores per node has a big influence on whether or not you're achieving linear or, in some cases, superlinear speed up. Of course, that's just a very brief summary. If you want to find out more details about the kind of problems we can solve using this method and the kind of implementation numerically, I'd encourage you to get hold of that paper in the International Journal of Computational Fluid Dynamics, published online earlier in 2019. If you have any questions about this work, please feel free to get in touch with me. There's my email address and my Twitter handle. I hope that was useful.